Homework 33, page 551. We are in section 8.8. Like I said, we're skipping those other ones. Oh, I didn't bother to tell you to skim the other sections. Okay. Skim. What was the last one we did? Yeah, we did 8.4 because that was partial fractions. So skim 8.5, 8.6, and 8.7. Just look at them. One of them is, you know, it's called strategy for integration, because by now you've seen, like, yeah, there's a lot of different things you could do, and sometimes you look at an integral and go,
what do you use?
I have to use
What
two
do
of
you
them.
use?
Yeah, do I have to use two of them? Whatever. This kind of breaks that down for you. You know, it gives you some hints and stuff. It's pretty good, right? Another way you could get all of that information is by just doing 1,000 of these, and then you come to the same conclusions yourself and go, oh yeah, I've gone down this wrong road before, I know. And so, you know, by trial and error, you come to the same information, but it's good to read. Okay, integration, tables, and computer algebra systems. You don't need to skim that one. I mean, you could. Actually, oh, that's part, is that part of that? No, who cares? Approximate integration. Now, this one's important. This is 8.7. But I just don't want to go into it. This is, and like I said, if and when I get around to doing the Fourier series project, I'm going to be doing something like that, because your signal, you have your piece of music and you have your signal, and when you look at it, it's just individual dots. That's all you have. And whenever you're actually doing integration in the real world, that's what your data looks like. You never have continuous data. Your data is always point sets like this. It's funny, my wife, who's, you know, a seismologist, had to actually compute an integral one day, and she was like, how do I do this? All I have is a point set. Oh yeah, right, of course, because it's just this, right? Yeah. Right? Yeah. So this is, oh yeah, I'll just, you know, multiply by dt and add them all up, right? Oh yeah, of course. But you forget that stuff, and there are better ways of doing it too, right? Like using these different points, you could say, well, what about a line going from here to here? What about a curve going between three of them? What if you use every 5 points and you find say a fifth order polynomial that, you know, does that, and then you integrate that guy? And that's what this is about. It's like there are different reasons why you might want to do different ways, and it turns out that some of the formulas turn out to be kind of easy when you actually compute what is this thing, like. And so you'll see when you skim this, like there are different ways of doing it, different reasons why you might want to use one versus another. Simplifications, if you're actually going to go and calculate it in, you know, tell a computer, here's my data, now I need you to compute the integral, this is the sum I actually want you to do. And so it's good stuff to know, but again, there are bigger fish to fry as far as I'm concerned. So today, we're going to be playing the game Converge or Diverge. And I had a professor who used this notation, and I love it, and I think he's the only person in the world who ever used this notation. So like, I love it, because it's like, instead of writing this sum converge, you just say, yep, boom, converges, right? And so I like that, and that's what I'm going to use from now on whenever I say, you know, does something converge or diverge. And so, okay, remember this one?
Yeah,
remember
this one did.
This one does, because this is the same thing. You could say this is the sum of x to the n, as n goes from 0 to infinity, right? And we found that that's the same thing as 1 minus x to the n over 1 minus x. In this case, the x is 1 over 2, right? Actually, this is what we're doing. I'm sorry. Right, up to whatever you do right there. Yeah. And then we say, okay, hold up. But when you take the limit, as this big N goes to infinity, then that's the same thing as the limit of this N going to infinity. And what's the limit of this as N goes to infinity?
Just 0.
It goes to 0. So you could say in the limit This thing goes to this. That's 1/2. That's the same thing as 2. And so this sum converges to a number, right?
Yeah.
But if I had done this,
No.
2, you could see when we do this, right? Raise 2 to the n, that ain't gonna converge. That's just gonna get bigger and bigger and bigger. It's gonna blow up. And that's what we mean by diverge, right?
Yeah.
That's one way something can diverge. Another thing that diverges is this. The limit as x goes to infinity. That limit does not exist. Why? Because this function does this, right? Now he's not going to one number. He's bouncing back and forth between infinity and negative infinity. But it diverges, right? Or we wouldn't say diverges with this because we're not talking about adding something up, but you would say the limit does not exist, okay? And so that could also happen with sums and stuff like that, in which case you would say it diverges. Okay, all right, so that was just a quick refresher talking about convergence and divergence. But this is gonna be the game all day long. Right now I wanna start with a limit. Here's a limit as x goes to infinity of e to the negative x. What is that?
It does this. It goes to 0.
It does go to 0. And let's think about what this function looks like. Right? That's e to the negative x. And you can see that as you go further and further this way, this goes to 0. Okay. Now, something unrelated. Let's do this. How about from 1 to 2 of x dx? Does this converge? Let me say.
Wait. Yeah.
Well, let's just think about it. Right. This is just the area under the curve.
Yeah.
Right. And if we think about this as just an area under a curve, we don't need to do any calculations. You could just say this. And you might be saying, what do you mean does it converge? It's just an area. Well, remember how this is computed, right? It's the limit of a sum. And so you're adding up infinitely many things. It may or may not converge, right? This is the same thing as the limit, as n goes to infinity, of the sum as little n goes from, say, 0 up to n, of whatever your function is, xi, delta x, right? And you're adding up infinitely many things. It turns out that in this case, right, you're adding up infinitely many things, but they get small enough, fast enough that they converge. So yeah, we would say this converges. We could do it explicitly, 1/2 x squared, up at 2, down at 1. That's 1/2 4 minus 1/2 1. 4 halves, that's I guess 3 halves. So this area here is 3 halves. It converges to 3 halves. So this sum, as you get big, you put bigger and bigger n's in there, it will converge to 3 halves. Okay, all right. Now, I'm not going to bother to tell you what this is or how we're going to compute it. But let's interpret it as an area. And let's say it's the area of this function, this very function right here, dx, from 1 to infinity. Do you think this converges or diverges?
No.
If we take the area under this curve.
You're basically adding smaller numbers as it goes on. So
That'll
probably
converge to
contribute.
the, yeah.
Yeah, it feels that way, right? Because let's think about what this means right here. This limit exists means that you give me any tolerance, epsilon, any tolerance, and that could be, let's say 1 over 10 to the 6. Okay, so that's 10 to the million. That's 0.00, a total of 1 million zeros, and then a 1, really, really tiny number. What this says is that if you give me that number, you want to get as close to million zeros 1, then I could find you an n such that whenever this is beyond n, then the distance from the function to the x-axis is less than that number. Really small number. And if your intuition tells you that that total area, if you were to add up that total area, that it's finite, that it converges, your intuition is correct. This does converge. We will talk about how we're going to compute this in just a minute. Okay, let's do one more. What is this? The limit as x goes to infinity of 1 over x. 0. Also 0. Okay, so let's draw it. Let's get the same kind of picture going on here. Also here, there's this. Okay, it goes to 0.
Yeah.
Right? Now, I'm wondering, here we go, from 1 up to infinity of 1 over x dx. So now we're talking about the area under the curve from here to here. What does your intuition tell you?
This number also converges.
Right? Because, right, you give me any epsilon. You give me any epsilon whatsoever. Now let's go for broke here. How about 10 to the 9? Right? 10 to 10 to the 9. That's 0.00. A billion zeros now. Not just a million. A billion zeros and 1. Then, if you give me that number, I could find an n so that this function is even closer. It seems like, since that's the case, it seems like this thing is getting really, really, really small, arbitrarily small. It should be a finite area, right?
Yeah.
And so you're telling me this converges, right?
Yeah.
That's what your intuition says. You're wrong. It diverges. What? Huh. Your intuition is often wrong when it comes to infinity. I'm going to explain why this is the case. Okay? So, first, let's look at the case where it converges. What we're doing here, this is indeed the same thing as just finding this whole area. But the way that we do this, the way that this is defined, is we say, okay, we're going to integrate from 1 up to some number n, e to the negative x dx. We're going to figure out what that is. Just like this. We're going to find this area first and get some formula with respect to n. Then what are we going to do? We're going to take a limit as that number, whatever it is.
A limit of a limit of some.
A limit of a limit of a sum. Yep. But the idea is, because this thing has an antiderivative, we can take its antiderivative, evaluate it at n, evaluate it at 1. And notice, this is always, no matter what that function is, you're going to get some antiderivative, evaluated at n, minus off whatever it is at 1. That's just some constant. You just have this, plus or minus some constant. And now, you have a function of n, and we're going to take the limit of that function, right? No matter what, this is what this is. So let's figure out what this is. What's the antiderivative of e to the negative x?
E to the x, right?
Negative e to the negative x. There we go. Now let's check it. Take the derivative of this. It comes out to e to the negative x. Negative x, negative 1. There's a negative in front.
Yeah.
The negatives go away, and you're left with the thing. Okay, we're good. Now we're going to evaluate that up at n and down at 1, and we get the limit as n goes to infinity of negative e to the negative n minus negative e to the negative 1. Yeah?
Yes.
Negative e to the negative 1. And I don't like that e to the negative 1. I'm gonna write it as 1 over e.
Okay.
Just because. I don't know. That's what I like. So limit as n goes to infinity of negative e to the negative n plus 1 over e. There we go. Now, what does that go to as n goes to infinity?
0.
Still 0. It's, you know, if we're thinking about this on an n axis, e to the negative n is up here. Negative e to the negative n is just the reflection. Still goes to the same place. Still goes to 0. So this is the same thing as 0 plus 1 over e. And so it converges to 1 over e. So that area, do you believe that this is valid? Right? Like, it's kind of like you give me any number and I'll tell you what the area is. Well, then I guess we'll just let that number get bigger, because that's just a function. At this point, this is just a function of n. And if you had told me 100, I'd just plug in 100 and we'd know what the area is.
Yeah.
If n were 1,000, well, I would have my function. I would plug in 1,000 and we'd know what the area is. And so if we could do that, it makes sense that you could just, if the limit exists, then you could find what it is as n goes out to infinity.
Yeah.
And that's how we define this. I'll put a definition up on the board in a minute, but this is the name of the game now. This is what we're going to do. Okay, so let's see what went wrong, or what goes wrong when we do the other one. From 1 up to infinity of 1 over x dx. Same thing as the limit as n goes to infinity of 1 up to n of 1 over x dx. So what's the antiderivative of that guy?
A negative. No, sorry.
It's what?
Log effect.
Right. Natural log of x evaluated up at n and down at 1, which is the limit as n goes to infinity of log n minus log 1, right? What's log 1?
0.
There we go. And what's that?
Infinity.
Does not exist, right? Because just think about log, right? Log goes up forever.
Yeah.
There is no limit. The limit does not exist. And so this diverges. Because the bigger n you put in, it just gets bigger and bigger, right? And so if this were the function 1 over x, the area from 1, if you just keep adding up this area forever and ever and ever, you're just going to get bigger and bigger and bigger. It does go to 0, but not fast enough. And so this is interesting now. Let's think about this. Let's say you have some function you have the integral from, I don't know, some number, we'll just call it a, up to infinity of some function of x dx. It's necessary that for this to converge, so I'll say, for this integral to converge, it's necessary. I don't know if I spelled this right. It's necessary that the limit as x goes to infinity of f of x equals 0. It has to be the case, right? Because if it went to any other number, let's say its limit was 1, well, obviously, then if you want the area of 1, like, that's going to be infinite.
Yeah.
Even if it's 0.01
It's still in there.
or 0.0001, well, if you're adding up infinitely much, I mean, it's not going to work. So it's necessary that this limit goes to 0 for that integral to converge, but it's not sufficient.
So something else has to be true as well.
Mm-hmm. It's not sufficient. You can't just say, well, limit goes to 0, it converges, you're good. No, it might not be. And we just saw a case where that wasn't. 1 over x goes to 0, but not fast enough.
What if it was like 1 over 2x, so it was faster?
Not fast enough, because 1 over 2x is the same as 1 over 2x, which is 1/2 log, and you evaluate that up at n and down at 1, say.
Yeah.
So
Still.
no matter what it is, if it was 1
Well,
over
if it's
10 million x, it's
Yeah, yeah. It eventually will blow up. So it's not enough to just multiply it by something. But,
Multiply it by n.
well, n doesn't exist really. It's not a thing.
1 over x.
Right, then you have a function in 2 variables. But what about 1 over x squared? From 1 to infinity. Let's try that one. Does that go down fast enough? It goes down faster, right?
Yeah.
Right, because this goes to 0 faster. So let's do that. Let's integrate from 1 up to n of 1 over x squared dx. What's the antiderivative?
It's x to the -2.
Yeah, that's x to the -2. So he would have to have been x to the what?
To the
Negative
or
one.
just negative
Negative
x
1.
to the -1, but negative.
Negative x to the -1, evaluated at n and 1. So we have negative n to the -1 minus negative 1 to the -1, which is the same thing as negative 1 over n plus 1. And what's the limit as n goes to?
It's 0, so then it's just 1.
And so the limit gives you 1.
Yeah.
And so this converges. In particular, it converges to 1. So this function, 1, you get out of 1. This one is 1 over x squared. It converges. And if you were to graph this on top of 1 over x, you'll see, because think about it like this. Plug in the 2 to 1 over x squared, and what do you get out?
1 over 4.
Squared. 1 over 4. Okay, so what pops out is a 1 over 4. Now let's graph 1 over x. And my claim is that he looks like this. Oops, that was terrible. Sorry about that. He's higher up, isn't he? Because plug in a 2, and he's not 1/4, he's 1/2, right?
Yeah.
So all of these are higher up. This guy goes to 0 faster, and it turns out that he converges, whereas this guy doesn't. And we're going to see 1 over x is kind of like, this is where everything falls apart. 1 over x is bad in every way we're going to talk about today. Okay, questions on this? Necessary, not sufficient, right? If you're trying to integrate something, you can look at that and go, does that go to 0 as we go to infinity? Yeah. Okay, then there's hope, right? There's hope that it'll converge, but we don't know for certain. Because 1 over x goes to 0, but he doesn't converge. So it's necessary, but not sufficient. Here's another example of something that's, or rather, here, watch this. Okay, let's play our game. Does this converge or diverge? So we're going to integrate from 0 up to infinity of the function e to the negative x plus 1 dx. Does it converge or diverge?
Oh. Wait. That doesn't go to 0.
It doesn't go to
So
0, does it?
It has to diverge.
Yeah, he's going to diverge. And let's see why in a second. But, I mean, well, here's why. Right? You take e to the negative x, which looks like that shifted up by 1, and he's not going to 0 anymore. That limit goes to 1. So you could stop right there and say, well, the limit as e to the minus x plus 1 as x goes to infinity goes to 1. So the necessary condition is not fulfilled. You could say he diverges. But let's compute it and just make sure and see that that's the case. So what's the antiderivative? So I'm going to do the n, and I'm going to take a limit. What's the antiderivative of this?
Negative e to the
Negative e to the negative x plus x as we go from n down to 0. And that's negative e to the negative n plus n minus negative e to the 0 plus 0. So that's a 1 minus minus 1 is plus 1. Negative e to the negative n plus n. Now we take our limit as n goes to infinity. And he goes to 0. He stays at 1, but this goes to infinity. So this diverges. All right. Okay. Necessary, not sufficient. So these types of integrals, right here, are called improper, like an improper fraction. It doesn't say like bad words or anything. It's improper integrals of type 1. Yes, there will be a type 2, which are a little different. So, and here's how we do them. So you have, here's one example of one. It goes from some number a up to infinity of f of x dx, and it's defined as the limit as n goes to infinity of a up to n of f of x dx if the limit exists. Otherwise it diverges and you've just written down junk, right? So like 2 up to infinity of x squared dx is junk. It's obviously gonna blow up. So otherwise you can compute it, and this is how you do it. The limit exists and blah blah blah. Or it could be from negative infinity up to some number a. And the way we do that, same thing. We're going to say, now we'll just change this to n down here. We'll go up to a here. And we're going to take the limit as n goes to what?
No. Oh, A.
Positive infinity?
Negative.
Yeah.
Oh, yeah.
Yep. Negative infinity. Or you could do negative n down here and make it go to positive infinity. It doesn't matter. It's the same thing, right? It's just negative. Okay? Okay. Now, here's another improper integral of type 1 from negative infinity up to infinity of f of x dx. Now, this is where it's tricky. This is where it's tricky. Because it's not, you don't plug in an n on the top and an n on the bottom and take the limit at the same time. You have to break it up. We'll get into this a little bit. Choose any real number a and break it up.
Oh, okay.
Okay?
So break
And
it
I'm
up
going to
into
go
two
from
functions.
n here.
Yeah. So if it's like a bell curve, then you would do this, right?
Yes. And then you go from a up to, and I personally, oh, I didn't leave myself enough room. I personally use different letters for this. Just to really, really show that we're not, like, these things are not related. Trust me on this. Limit as n, in this case, goes to what? N goes
To negative infinity.
negative infinity. And here, the limit as m goes to positive infinity if both of these exist.
That exists. Distribute.
Distribute the both. Okay? So, and what I mean by that is that these conditions, right? Like that you take the limit like that, and if that exists, and that is, if either of them don't exist, then this thing doesn't exist. Let's do an yeah, actually, let's do it this way. So, let's suppose that we did it the way that you would expect, the way that I would expect, and say, okay, negative infinity up to infinity of f of x dx why don't we just define it this way? The limit as n goes to infinity from negative n up to n. Do the two limits at the same time, right? Well, let's see what happens. Let's suppose that big F is the antiderivative of little f. So we have big F x evaluated up at n and down at negative n. And what we have, and of course, yes, we're going to be taking the limit as n goes to infinity. Everybody with me?
Oh, that's, yeah.
Right?
Okay,
So,
infinity minus infinity.
and so, let's just see what happens. And we have a plus c there, but when we do the minusing, the plus c is gone, so I'm not bothering with the plus c.
Yeah.
The limit as n goes to infinity of big capital F n minus big capital F negative n. If this is an even function,
Oh,
right? Like x squared is an even function.
Yeah.
So negative, you plug in a negative, it's the same thing as if you plugged in a positive, right?
Yeah.
So if this is an even function, then you get fn minus fn, which is always 0. Always.
But it's infinity. So it's infinity minus infinity.
Well, or is it, right? And that's what I'm saying. Do you do this first and then compute the limit?
Oh, yeah.
Or do you do
Yeah.
this? And so this takes care of all of that stuff. Like, because this will always be 0. Limit as n goes to infinity. This is the same thing, so it's 0. The limit of 0 is 0. Or should we compute them and make sure? But even if you do, it's going to give you the exact same thing. It's going to give you a 0. Or will it? What if it's an odd function? If it's an odd function,
Then
the
it's
negative
plus.
becomes
Oh,
that, and then it's 2 times that. Is that right? And this is actually a thing. This is a thing. This is called the principal value. The principal value of a function. You just do this. The principal value of f is when you take the limit at the same time. If it's even, it comes out to 0. In fact, there's different kinds of principal values. This is called the Cauchy, named after like Jean-Baptiste, I think is his first 2 names. You know the French, they have like 1,000 names. But Augustin Cauchy, or Augustine Cauchy.
Cauchy Schwartz thing, or is that
Yep. Same Cauchy. Everything's Cauchy after a certain point. Everything has the name Cauchy in it. And this is the Cauchy principal value. And it's useful for certain things, but it's not how we're going to compute areas. So, it's something else. Take analysis and figure it all out. Have fun, because when you get to that point, boy, are you in for a ride. But this is how we're doing this. This is how we are going to define this right now. We're going to say break it up into 2 limits, and if either of them blow up, then they don't exist, and so this diverges. Done. Even if that one goes to positive infinity and that one goes to negative infinity, we're not going to say, oh, add the infinities and it's 0. No, we're not going to do that. If either one of them or both of them go to infinity, then you're done. Or if the limit doesn't exist, right? So like the limit as n goes to infinity of sine n, does that limit exist? No, he bounces back and forth between 1 and negative 1 forever. It does not exist, and therefore does not exist. Okay? So that's how we're going to play this
Would it
game.
not just be 0 because there's just as many positive ones as negative?
Well, the
Well, this is what, right? Like, but that we're not summing them. If we were summing them, maybe you can make that kind of argument. But here we're just saying what happens as you go to infinity. Well, not one thing. It's not converging to one value. He's bouncing around between different values forever. And so he doesn't converge, and so limit doesn't exist. He's not getting closer and closer to some value. So that's just definition of a limit. Maybe something else is happening. Maybe if you add them up, you can make an argument that it's 0, but that's not what we're doing. We're just talking about a limit. And so, everybody good with this?
yes.
These are improper integrals of type 1, and I want to do one here. So
there's 3 types of improper integrals of type 1.
yeah. Anything with an infinity in the limits of integration,
Yeah.
the domain. We'll say that. If you're integrating out to infinity or down to negative infinity or to both, then we call that type 1.
Okay.
And here's one here. We want to compute that guy. And this guy looks like this. Like a bell curve, but not a bell curve. Very similar, or kind of. And I can see that as you go in either direction, this thing goes to 0, so there's a chance.
Yeah.
Right? Okay, so I'm going to say, by definition, we split this guy up. And I could split him, like I'm telling you, we could use any real number. I'm going to choose to use 1. I'm going to say, let's integrate from negative infinity up to 1 of this function. And then we'll go from 1 up to infinity for that guy. But we're not going to write infinity, are we? I mean, we could, and then take another step. Or I could just say, let's go n here and m here. And I want to take the limit as n goes to negative infinity, and the limit as m goes to positive infinity. What's the antiderivative of this guy?
Oh, it's tangent.
Not tangent.
Oh, arctangent.
Arctan. Okay. So this is the limit as n goes to negative infinity of arctan. I'll do it this way. N and 1. This is the limit as m goes to positive infinity, arctan evaluated at, oh, whoa, 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 whoa. Look at what I did. Did you see what I did?
Oh.
Did you see what I did? I said n and 1, n and make sure you're not messing that up like I just did. All right. Okay. So now let's find this difference, and then we'll compute a limit. So limit n going to negative infinity. Arctan 1, I'm not even going to bother to figure what that is. Why? You'll see in a second. Minus arctan n plus the limit as m goes to positive infinity of arctan m minus arctan 1. Okay, arctan.
That approaches pi over 2, right?
Yeah, and let's just think about this. This is one of those I told you that you should be able to draw this in your sleep. Shows up a lot. This is arctan, and we have two asymptotes. The top is pi over 2. The bottom is negative pi over 2. And so as n goes down to negative infinity, arctan goes to negative pi over 2. This guy doesn't change. He's still just arctan 1, right? So, yeah, it is, but I'm writing it like this for a point. So minus arctan negative pi over 2. Be careful, right? You got that?
Yeah.
Minus arctan n. N is going to minus pi over 2. So this value goes to negative pi over 2, but we're minusing it off. Okay. Now, arctan going positive infinity gets closer and closer to pi over 2. Minus, he's not changing, arctan 1. Now I could have integrated from n up to smiley face up to n, and we'd still have arctan smiley face minus arctan smiley face. This is why it doesn't matter when you're integrating from negative infinity to infinity.
Oh, it doesn't matter what one you choose at all.
Yeah, it doesn't. Because they're going to cancel out like that when you do that. Now what do we have? Minus pi over 2.
So just pi.
Which is just pi. So this converges to pi. The area under that guy is pi. It's kind of cool.
So, yeah.
Now we cannot do this one. You need at least multivariable calculus to be able to do this one. It might actually be in your book somewhere. But negative infinity up to infinity of e to the negative x squared dx, which is a bell curve, an actual bell curve. It looks like this, but is truly a bell curve. Also, Gaussian distribution turns out to be square root of pi. Yeah. Talk about irrational. Like if pi weren't irrational enough, now you took the square root of it. Yeah, way irrational. But yeah, so that's just so you know. But you need like you need to. There's some nifty tricks you need. You have to turn it into a three-dimensional problem and then bring it back. Yeah, it's pretty cool how you do it. Okay, so that's that. Everybody got that?
Yes.
Okay. Here's something else. Now let's compute this interval. 0 up to 1 of 1 over root x dx. Do you see any problems with that?
You can't plug in 0.
Yeah, like if you think of, let's graph what this thing looks like. Probably looks something like this. Right? Plug in a 1, you get out a 1. And just to note, right, if this is 1 over x right here, this is 1 over x. If you took the square root of it, used to be you plug in a, let's say you plug in a 4, you get out a quarter. Now, if you plugged in a 4 into this one, you'd have 1 over root 4 is 1/2.
Oh, so it's slower.
It's higher.
It like approaches slower than 1 over x.
Oh, slower, yes, 1 over root x over here. But over here, he's lower.
Yeah.
Right? He's lower over here. Because it used to be plug in a 1/2, you get out a 2. Now you plug in a 1/4, you get out a 4. Now with this guy, you plug in a 1/4, you get 1 over root 1/4, right?
Yeah.
Which is 1 over 2. 1 over 1 over 2, that's 2. And so you're actually lower, and that's what I'm trying to show here.
Yeah.
I'm doing a poor job of it. Over 2. So the root, right, it brings them down here, but brings them up here. So you're screwed over here. Like you're not going to converge over here, but we don't care about that. We care about what's going on here. And now we're talking about this area, right there. Right?
Oh,
We're
yeah.
integrating from 0 up to 1. So there's a chance, because we didn't talk about this, but like I said, 1 over x is the worst case scenario. And actually, I should have gone ahead and done this.
The inverse might then.
Let's go 0, 1 of 1 over x dx.
So take the 1.
You would think, yeah, and that's what we're going to end up doing here, right? I'm sorry, I should have thought that through. But anyway, so we still have a problem here, right? Because we're still talking about an infinite area. It's possible that this area, like obviously this goes up, but the question is now, how fast, how fast is this thing approaching the y-axis? Because if he's approaching the y-axis fast enough, it's the same kind of thing like when we had 1 over e to the x. He's going down really fast. Or I'm sorry, well, yeah, 1 over e to the x is e to the negative x, right? He's going down fast enough so the area gets small enough that it converges. Whereas 1 over x did not. He's going there, but not fast enough. And so now here's the question. The same kind of thing, and you can see if you flip this, it looks the same, doesn't it? Right? Like, how fast is this thing closing off that gap? And the way we do this, it's very similar. We find the problem place, and we're going to take a limit. I'm going to say, so there's a problem here. And it's not enough to just try to plug in values. We've got to take a limit. And so I'm going to say, okay, let's take the limit. We'll call this one n, because that's the problem place. There's no problem here at 1. 1 over x, I'm going to rewrite that as x to the negative 1/2, because I'm doing integration. It's going to, and I'm going to take the limit as n goes to 0. You take the limit as it goes to the problem place.
Yeah, okay.
And in particular, as it goes to the problem place from, since this is this one, as we go in this direction. So from the right. Okay, so what's the antiderivative of this?
No. 1/2
1
x.
half x to the 1 half.
Is it 1/2 x to the 1/2?
Yeah.
Yeah.
You sure it's
Oh,
a half?
2x.
Yeah, I know, right?
Yeah.
I think I did that too, right? It should be, let's try 2x to the 1/2. Now, the half drops down, kills the 2. Then you get the -1 off of it, giving you -1/2. Okay. So this is 2x to the x to the positive 1/2. Or how about let's just write that as 2 root x. Evaluated at 1 and n. Limit as n goes to 0 from above. We have 2 times root 1 minus 2 times root n. Any problems there?
Yeah. Wait, open is 0. So no.
No, we just get 2 and 1. N goes to 0. No problem there. And we're going to 0 from above, so you don't need to worry about negative. And that doesn't matter anyway. But this thing goes to 0, and so it's just 2. And so it converges to 2. So this area right there, and it's the same kind of thing. This guy is going towards the y-axis fast enough that that area converges to a number. Does that make sense?
Yeah.
Okay.
If it was just 1/x, I'm guessing I wouldn't.
1/x is the worst case scenario. So let's do that one now. Okay. So same setup here. Only now we have 1/x. Okay, same thing. We're going to say that's the limit. The problem area with 1/x is this, 0. And so 0 is the problem place. I'm going to go n up to 1/x dx, which is the limit as n goes to 0 of log x evaluated at 1 and n, which is the limit as n goes to 0 from above of log 1 minus log n.
And log,
That's 0 minus that limit.
log of 0 is just, can't do that.
You can't do it. There is no limit because log, as you go to 0, does that. Goes to negative infinity. Negative infinity gives you a positive. Who cares? It's infinity. It doesn't converge. So that's the worst case scenario, right? And you can see that if you have a function that goes either way, right? If he goes bigger this way than 1/x, well, he's not going to converge that way. But he might converge this way, as was the case with root. The root one gets there closer. But as far as these functions are concerned, 1/x is the worst case scenario because he diverges this way and he diverges this way. So, yeah. Okay. Now here's a tricky one. Ready? You guys ready to move on?
Yes.
Questions about what we've done thus far? Okay, let's do this. This is straight out of the book, and I tried. I wrote one and did it. I had it all written out, and was like, "Yeah, I'll do it different. So that way, it's not the same one that's in the book." And then I got to the end. I was like, "I see why they did the one that they did," and I just decided to do this. Okay. Do you see any problems there?
Yeah, you can't plug in a 1. Wait, but
Yeah, we're integrating over.
The area.
Yeah, and so think about it, right? You have this function, it's just 1/x, but he's been shifted over to 1, and so he does this and does that. And if you weren't paying attention, let's just see what would happen if you weren't paying attention to that. You'd say, okay, what's the antiderivative of this?
Natural log of x minus.
Natural log of x minus 1. In particular, I always forget this, it's the absolute value of it. Yeah. And so you evaluate it at 3 and 0. And so that's the same thing as log absolute 3 minus 1 minus log absolute 0 minus 1. That's a 2. And it's just a plain old 2. 0 minus 1, that's log 1,
0.
which is 0. And so you conclude log 2. Cool. Okay, we're done. But you didn't take this into account, right? So we're going to do the same thing as we do with... We have to take into account where this thing blows up. And we know it blows up at 1. And so we're going to integrate from 0 to 1. 1 over x minus 1 dx. And then say 1 up to 3. 1 over x minus 1 dx. And then we say, oh, well, we have a problem here, so I'm going to go to m. Here I'm going to go to n. And we're going to take the limit as n goes to 1 from the left. Usually that's not going to matter. It might matter. Like, it might change the sign of your answer. Here, we're going from 3 down to 1, so we're going to approach 1 from the right. Usually won't matter. Usually, if you're doing something like this, it's going to blow up, and so who cares? But anyway, so let me just show you how I would work on this. I would say, okay, let's do this one first. Antiderivative of this is log x minus 1, evaluated at n and 0. So we get log n minus 1 minus log 0 minus 1, okay? Take the limit as n goes to 1 from the left, we get a 0. Log 0 blows up. Blows up, diverges. I don't bother with anything else. Because the same kind of thing happens. They both have to converge for this to converge. And you could play a game.
Makes sense.
And physicists love to play this game where they're like, well, that goes to positive infinity, that goes to negative infinity, add them together and it goes away. In certain contexts, it makes perfect sense to do that. But that's not what we're talking about here. Like in our class, what we're dealing with is, does this converge? That integral does not converge. So we're done. This diverges. Boom. I'm done. Cool? Everybody okay with that? Okay. Okay, that's cool. So this is what we call it. This type of integral is an improper integral of type 2. And that's where you're trying to integrate over singularity. Singularity is division by 0. Improper integral of type
Wait, so
2.
isn't the one we just did like that?
Yep.
Oh.
Yeah, that's what I'm saying. So we've now played with it, and let's nail this down. So first off, f needs to be continuous on the interval a to b. Oops. Why did I do that? Interesting. It's continuous on this interval, but discontinuous at b.
Oh.
Right? So in other words, you have like a 1 over x minus b. You're fine everywhere except for b. So then, this integral from a to b, we will define as the limit as n goes to b from the left, a up to n f of x dx, if it exists. Otherwise it doesn't exist, it diverges, and we're done. Okay? Now, suppose that f is continuous on a b, but discontinuous at a. Then the integral from a to b, f, is the limit, n goes to a from the right, because I want to make sure about this, ab, there's your interval, and yeah, we care about the limit as we go from the right of n up b f of x dx if the limit exists.
Yeah. Okay.
Now, f is continuous on AB, but discontinuous at some c in the interval a to b. Not a, not b, but some c that's in between. Notice I'm using hard brackets here, soft brackets here. So that c is some number that's not a, in other words, a strictly less than c, strictly less than b.
Yeah.
Right. Then a b f of x dx is equal to, we're going to split it up. A up to c, c up to b, f, f, and we're going to take the limit as, oops, yeah, so the c is the problem, and so we're going to call it an n. C is the problem, I'm going to call him an m. And we go, n goes to c from the left. And here the limit as m goes to c from the right. If both limits exist. If either one of them blows up, then the whole thing blows up and we're going to say, nope, can't do it, diverges. Everybody with me?
Yeah.
Okay? Alright, now here's something actually useful. Okay, like a lot of this is just like, this is just the game we're going to play. We could, we could very well just define it as, we'll take the limit of the, as well as it goes. I mean, like with negative infinity to infinity, like why don't we just do it, at the same time, from negative n up to n, and then take the limit as n goes to infinity at the same time. We could do it that way. That's not how we're doing it. We're choosing not to do it that way. We have a choice,
That
we're
didn't
choosing
work
not.
today.
What?
Did that way work? I thought that way didn't work.
Right. I mean, but you could define it that way. This is what I'm saying. Like, now we're dealing with infinities. Like, well, what do you mean by that? Are you plugging in an infinity? It takes... So, this is just how we're going to deal with such integrals. And we're going to say, like, if, when you split it into two integrals, if one of them diverges, then we're just going to say they both diverge. Or like that everything diverges. It's junk. You can't trust your answer. Okay, now this is useful. This is called the integral comparison test. And this is when you have functions, f and g, and we're going to suppose they're continuous on the interval where everybody's bigger than or equal to a. So, in other words, the interval from a to infinity. Okay? And on that, what do I have? We have this. So g is less. On some interval, g is less than f. So imagine, here's just a picture, it might be suggestive. You have some a, and you have some function that does this, and then you have some function that does this. Right, so here's your f, and here's your g. This type of thing. Okay, maybe it looks like this. Well then, I'm going to put it this way. I'm going to be sloppy with my writing here. F converges, then the integral a to infinity of g converges. Right?
Yeah.
Think about it, right? You have your f, and you know that this area is finite. Well, if your g is less than it on the same interval, then he's also finite. And so, if that converges, if f converges, G converges. Now, another thing's true. If the integral of G diverges, then the integral of F diverges. Because, again, here's your G. G is the lower one. And that area is already infinite. So if F is bigger than him, then he must also diverge. Right? Okay? And really, you could see it this way. Another way that I could have stated these two statements is to just say, well, if 0 is less than G less than F, then this is true, right?
Yeah.
A up to infinity, A up to infinity.
Yeah.
And if this diverges, then that diverges, right?
Yeah.
Now, notice what we don't have here. If, like, suppose this one's infinite, can you say that that's not infinite?
No, it still might.
No, it might be, right?
Yeah.
Like,
Like the 1 over 2x.
yeah, there you go. 1 over 2x is less than 1 over x. 1 over x is infinite, and so, no, you can't conclude that that one's necessary. But what you can conclude is that if this guy's infinite, then so is that guy. And if this guy's finite, he goes to some finite number, call it n, well, then he's less than that. He also converges, right? So that's what this is. Everybody got that? Okay. Here's an example of how we're going to do this. Here's 2 examples of how you could use this. And then I'm going to show you something I think, personally, is pretty cool. So here's how you're going to do it. This is number 50. It says to use the integral comparison test to tell whether this is convergent or divergent. Okay, so 1 up to infinity of 2 plus e to the negative x over x. So, we're looking at this. Here's my function. I'm just gonna rewrite this function. I'm gonna say, there's my function f, and it's 2 over x plus e to the negative x over x. Sometimes that's the first thing you want to just rewrite it. This is some function. It does something, I'm guessing, it looks like it goes to 0, right? As x gets really, really big, it should go to 0, so it looks something like this. Now the question is, does it feel like this thing blows up? Or does it converge?
I don't know.
I'm integrating. Let's look at this. It's the same as integrating these guys right here.
Oh.
Does it look?
Yeah, it definitely.
It looks like this thing is going to cause a problem.
Yeah.
Now, this is, I mean, there's 1,000 ways you could approach this. Usually, if you have a feel for it, and you're like, because this is going to change how you're going to do this. It feels like, to me, this thing blows up.
So you would just start with that.
So what I'm going to do is try to find a function that's smaller that also blows up. And here's the thing. This is you can make this really hard on yourself, but watch this. When you're on 1 to infinity, is this always a positive number?
Yeah. Yes.
It's always a positive number?
Yeah, so it's
So
always
this
bigger.
thing is always bigger than or equal to this thing?
Yeah.
Yeah, okay. And so now that's the thing I'm going to use. I'm going to say, okay, well then 2 over x is always less on this interval, and that's where it gets tricky, is less than 2 over x plus e to the negative x over x. And so if I could show that this blows up, then this blows up. And indeed it does, because you integrate from 1 up to infinity of 2 negative x. It has to be less than or equal to the original thing that you had, negative x over x from 1 to infinity. You do your thing, you get your 2 log up at n, down at 1, and you get 2 log n, limit as n goes to infinity, blows up. And so that one's smaller than that one. If this one blows up, then the bigger one blows up, and so we're going to say it diverges.
Yeah.
Now, if you had thought, well, and so this is, if my intuition was this converges, then what I'd be looking for is something that's bigger, right? Because if I'm trying to show that f converges, then I want to find something bigger that I can show converges even easier, right? So that changes the game. And sometimes that's the case. You look at it, you're like, this looks like it converges to me. And so then you try and you try and you try, and you can't really find, nothing's working out. And so then you go, well, maybe my assumption was wrong in the first place. Maybe this does diverge, and I should try to find a smaller function. So it takes some finesse. It takes a lot of finesse, actually. And like, you do this a lot in analysis. This is like the name of the game for analysis. So we're going to play the same game here. We're going to say, here's an example. We want to know, does this converge or diverge from 0 up to infinity of 1 over x cubed plus 1 dx? Does it feel like it converges?
Yeah, it's just bigger than 1 over x squared.
It's actually, is it bigger?
Well, like the bottom is gonna be.
Yeah, and so, okay, here's the thing. This thing looks like this. And there's a couple ways you could go with this. You could say, well, you know what? In fact, we just did one like this. 1 over x squared plus 1.
Yeah.
And since the denominator's smaller, then this is bigger, or is it? And this is where it's bigger whenever you're bigger than 1. Because that's bigger. But then when you're over here, so this is 1 over x cubed plus 1. And indeed, this thing is bigger when you're past 1. This one is 1 over x squared plus 1. But it's smaller down here. But we don't really care. We don't really care. We could just say, well, okay, hold on. From 0 to 1, 1 over x cubed plus 1 dx plus 1 to infinity, 1 over x cubed plus 1 dx. This is obviously finite.
Yeah.
Obviously. Like, there's no division by 0 or anything like that, so this is finite. So now we could just work with this guy and say, this guy's, so on 1 to infinity, this is true. Then you could say, okay, so from 1 to infinity you get that. This thing works out to arctan n minus arctan 1.
It's just pi, right?
Take the limit as n goes to infinity. This is pi over 2 minus pi over 4. Pi over 4. So this part converges. This is finite, plus something that goes to pi over 4 is also finite, so this converges. It's one way you might do it. Another way you might do it is just say, and this is, so that works, that's cool. But another thing you could do is say, hold up. I feel like this converges, so I need to find a bigger function that converges. If you make this denominator smaller, you make the function bigger.
It's just 1 over x. That's
Yeah.
a lot easier.
And then, yeah, and so, I'm telling you, there's 1,000 ways of doing this. There's infinitely many functions that work, you know, and so this would be much easier to just integrate. Problem is you're going from 0 here, that may or may not, so go ahead and split it up, right? That's finite. This is good. So this is the question right there, right? So I'm just going to integrate from 1 to infinity of both of these guys, show that that's finite, state that that's finite. There's no division by 0, so we're fine. And so there you go. It doesn't need to be 1. It could have been 100, right? You're fine.
Yeah.
Okay? That's the cool thing about this. An arbitrarily large number, this is still finite. Okay? Okay, now let's do something cool. Integral comparison tests work for things that aren't integrals, too. So recall, we just did this. 1/2 plus 1/4 plus that, up to 1/2 to the n plus, and so on, I said converges, right? We did that earlier. We saw that it converges to 2. And I've said before that 1 plus a half plus a third plus a fourth plus 1 over n, I told you that that diverges. Oh, and keep going. Now we're going to show that it diverges. We haven't seen a proof of this. You're going to see one right now. What we could do, it's like there is no integral here. That's just a sum. How are you going to compare that to an integral? Well, let's reinterpret this as an area. And so what I'm going to do, and I could do this anywhere, but I'm going to choose to do it right here. I'm going to say, let's start at 1. And let's say 1. This is an area. If I go over 1, then now it looks like a rectangle. It's actually a square, right? What's the area of this rectangle?
Just 1.
1 times 1 is 1. So this is, I'm going to call this, area 1. And that's the same thing as this, area 1. Now I'm going to come over here, we're at 2, and I'm going to go down to 1/2 and say, okay, 2, shoot. Try to do this right. 2 over to 3 with a height of 1/2. He has a base of 1 and a height of 1/2, so his area is what? 1/2. So this is the same as area 2. I'll do this one more time. Here, at 3, I'm going to come down to 1/3. Draw a line straight over to 4. And now what's the area of that? 1/3. It's the same as this. And we'll do one more here. At 4, I'm at 4, so I'm going to go up to 1/4. And then come down here to 5. And so on. And then I get to n, and I go up to 1 over n. And then draw a line over a length of 1, and that area is 1 over n. This area has a height of 1/4, width of 1, so that area is this right here. And now I've just reinterpreted this sum as a sum of areas, right?
Yeah.
Is there a function that you know of that has this behavior where you plug in a 1, you get out a 1, you plug in a 2, you get out a half?
1 over x.
Plug it, 1 over x, right.
Oh.
And so, let's just see what happens when I do this. Now you'll notice this area is larger than the integral of this function, right?
Yeah.
Okay, so let me rewrite this. So the area 1 plus 1/2 plus all the way up to 1 over n, and we keep going, is less than, obviously, or no, greater than, yes, it is greater than, it's bigger than the area under the curve from 1 up to infinity of 1 over x dx. But we know that that diverges. If that's infinite, then this must be infinite. And since we've already shown that that's infinite and we're running out of time, I'm just going to do this, right? This diverges, therefore this diverges. Pretty cool, huh? One more thing. So now we've proven, this is the harmonic series, we've proven that the harmonic series diverges, if you believe all this. There's one more thing that we talked about. You remember in Algebra 2, I told you to complete the square with this guy right here. And I said, gamma is a constant.
Oh, yeah. That was on the
And
final,
it's approximately equal to like 5.4 or something. Right?
Yeah.
Gamma is this area. If you add up all of these guys here, this area here turns out to
like the air.
converge. And so how do we compute that area? Well,
Just minus.
This is, yeah, so we take this, whatever it is, which is, I'm going to rewrite that as the sum as n goes from 1 up to infinity of 1 over n. And then we minus off the integral.
Wait,
From
wouldn't you
1.
minus off that from wait.
The full.
Oh yeah.
Which we know is the same thing as, and actually, if we do like this, and like this, then we could take a limit as n goes to infinity like that. Which we know is the limit n goes to infinity of n goes from 1 up to big N, 1 over little n, minus, that would be log n minus log 1. Log 1 is 0, so this is just log n. And there, that's gamma. And he shows up everywhere. It shows up everywhere. Whatever this number is, this does converge. This converges to a value, gamma, which is approximately 5.4 stuff, blah, blah, blah. Nobody knows whether or not it's rational or irrational or transcendental or algebraic. Nobody knows. If you find that out, I'm sure you could get a tenure track position at any Ivy League college. So go to work, guys. And so it's just interesting, yeah. So my point for bringing all this up, one, is you've seen gamma before. I wanted to show you what it is, how we define it. It's defined this way. This limit converges. And also, just to show you, the integral comparison test is not just used for integrals. If you could be tricky and rewrite a sum as areas, then you could use an integral comparison test to prove, indeed, the harmonic series diverges or whatever you want to prove. And actually, that's a huge thing in analysis, because in analysis, one of the big questions you have is you have some sum of something, and you want to know, does it converge or not? Think, I told you, an cosine stuff plus bn sine stuff, or think the sum of f x0 n factorial x minus x0 to the n. This type of stuff, right? Like really, really, really important stuff. We want to know, does it converge or not? Is this junk when I go to plug something in or not? One way you could do that is say, well, if I could find an integral that's bigger than it or less than it with some function, then I could show that it converges. And it's really useful, and it's one of the many ways that you would deal with trying to find out whether or not a series converges.
Yeah.
That's all I got, guys.